Section 8.1, Introduction to Radical Expressions. Radical expressions are algebraic expressions that involve square roots. A square root of a non-negative real number a is a number that when squared is a. For example, the square roots of 9 are, what number can you square and get 9? Well, if you square 3, 3 squared is 9, so that works. But there's another one. What's the other one? Negative 3. Negative 3 squared is also 9. And 3 squared is 9. So positive 3 and negative 3 are square roots of 9. The symbol, that symbol, is called the radical sign. It stands for the positive or principal square root. For example, the square root of 9 is 3. Just 3. You won't only want the positive one. But if you put a negative in front of that principal square root sign, you can make the answer negative. Then you would have negative 3 as the answer. But you have to put the negative sign out front, because that radical sign says take only the positive square root. The number under the radical sign is called the radicand. We will focus on radicals with non-negative radicands. We don't want to take the square root of negative numbers like negative 4. That's for another class. A whole number is said to be a perfect square if it is the square of another number. So list 5 perfect squares. Well, 2 squared, that's 4. That's a perfect square. 3 squared is 9. We already have that. 4 squared is 16. 5 squared is 25. Those are all perfect squares. 6 squared is 36. 7 squared is 49. Can you keep going? 8 squared is 64. 9 squared is 81. Keep going. 10 squared is 100. 11 squared is 121. So let's find the values of the following radical expressions. The square root of 64, remember, we want to take the positive square root, so we get 8. The square root of 49, without that negative in front of it, would be just positive 7. But the negative forces it to be negative. Negative 2 times the square root of 100. The square root of 100 is 10, and then we want to multiply that by the negative 2, so we'll get negative 20. 3 times the square root of 144. What's the square root of 144? Your calculator has a radical button, so for most calculators, you press second and then the square root, and the square root of 144 will get you 12. 3 times 12, 36. Try that with your calculator and see if you can make it work. Some numbers are not perfect squares, so their square root is an irrational number. An irrational number, remember, is a decimal that does not stop and it does not repeat a pattern. So the square root of 2 is 1.4142, What's the next digit? I have no idea. It doesn't ever stop and it does not repeat a pattern. The square root of 10, 3.162276 something, I don't know what. So let's use our calculators to find the square root of 20. You should be able to figure out how to make your calculator take a square root. So we have the square root of 20. We want to round it to the nearest thousandth. That's 3 decimal places. So 4.472. 3 decimal places. We're going to put those wiggly equal signs to show that 20 is approximately 4.472. 5 radical 7. You should be able to put that in your calculator, just like it's written, 5 radical 7. Do you get 13.2287? we'll round that to 13.229, and that's our approximate answer to 5 radical 7. The operations of squaring and taking a square root undo each other. So 5 squared is 25. We squared 5. Now let's take the square root of 25. We get 5. Squaring and square rooting undo each other. Non-negative real number a, the square root of a, that quantity squared, should get us what we started with. It should just give us a. For any non-negative real number a, if we take a and square it first and then take the square root, we should still get what we started with. We should get a. So we can do this. Let's do it step by step, and then we'll use that idea first, or use that instead. So the square root of 4 is 2, and 2 squared is 4. The square root and the squaring undid each other. You get what you started with, which is 4. The square root of 11 is I don't know what, but once you square it, you should get 11 back again, because the square root and the squaring undo each other. The square root of 5 squared, that's the square root of 25, and the square root of 25 is just 5. So you get what you started with, number 5. The square root of 7 squared is 7. You can think of it as the square root of 49, which is 7, or you can just realize the square root and the squaring undo each other, so we get 7, what we started with. Assume that all variables represent non-negative numbers in this section. That will simplify everything for us. So if we have the square root of a times b, that's the square root of a times the square root of b. Let's check and see if that makes sense. The square root of 4 times 9, that is the square root of 36. The square root of 36 is 6. We could have taken the square root first. So what's the square root of 4? It's 2. What's the square root of 9? It's 3. That gives you 6. So it doesn't matter whether you take the square root and then multiply, or you multiply and then take the square root. It is usually easier to take the square root first, if it's possible, and then multiply, because the numbers are smaller. But a lot of times when you factor a number such as 18, you can't factor it into two numbers that you can take the square root of. So what can you factor 18? It could be 3 times 6. I can't take the square root of 3 or 6. That's not good. It could be 2 times 9. Ooh, I like the square root of 9. Let's write that as the square root of 2 times 9. The square root of 2 I can't really do anything with, but the square root of 9 is 3. Now this is where it gets a little confusing. If I write it as the square root of 2 times 3, square root of 9 is 3, that looks a little confusing to me. I'm afraid that I'm going to draw this line either too short or too long and not really know whether I'm taking the square root of 3 now or not. If I put the 3 out front, that avoids confusion. Put the 3 out front. You have already taken the square root of 9. That gave you 3. You don't need to take the square root of again. So put the 3 out front. 3 radical 2 will be our final answer. So when we factor our numbers here, we're looking to factor it for one of the factors to be a perfect square. So 48. 48 is 2 times 24, but that doesn't help. You can't take the square root of 24. It's 4 times 12. That's nice, because I can take the square root of 4. But you know what? 12 is 3 times 4. I can take the square root of that 4 too. I'd rather factor it as 4 times 4 is 16 times 3. Now that one appeals to me, because I can take the square root of 16. I can't take the square root of 3, but I don't care. The square root of 16 is 4, and that leaves me with 3 under the radical. So the final answer is 4 radical 3. You can prove using your calculator that the square root of 48 is the same thing as 4 radical 3. First, take the square root of 48. You get 6.9282. Then take 4 radical 3. 4 times radical 3. You get 6.9282. You get the same decimal answer. So those are equivalent. 4 radical 3 is the exact answer. That is approximately equal to 6.928. That is an approximate answer. We usually want exact answers. Let's simplify this negative 2 radical 50. We're going to have to factor 50. 50 could be 5 times 10. That doesn't interest me because I can't take the square root of 5. I can't take the square root of 10. It's 25 times 2. Oh, I can take the square root of 5. Or 25, it is 5. You want to factor it into something you can take the square root of. Factor it into the largest perfect square that you can times whatever's left over. Negative 2 square root of 25 times the square root of 2. Negative 2 times the square root of 25 is 5 times the square root of 2. You can multiply that 2 and the 5 together, and we have negative 10 radical 2. That's our exact answer. Square root of 45. We're going to factor it into what we can take the square root of, the largest perfect square factor. 45 is 9. 9's a perfect square, times 5. Square root of 9 is 3. I can't take the square root of 5, so it has to stay under the radical. So our simplified version is 3 radical 5. 3 radical 24. We're trying to factor 24. What perfect square is a factor of 24? But 4. 4 times 6. 3. Square root of 4 is 2. You can't take the square root of 6, so it stays under the radical. 3 times 2 is 6, radical 6. That's our answer. Square root of 20. Let's take a moment. I keep talking about these perfect squares. What are the perfect squares? 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. We've talked about these. 6 squared is 36. 7 squared is 49. 8 squared is 64. We want to find a factor involved. We would like for one of these perfect squares to be a factor of our number. So the square root of 20, which of these perfect squares is the factor of the square root of 20? 4 is. 4 times 5 is 20. The square root of 4 is 2. You cannot take the square root of 5, so it has to stay under the radical. Now, it is awfully tempting to do some sort of cancellation here, but be very careful. The 5 is under the radical. It is really not a 5. It's a square root of 5. The square root of 5 is 2.236. You can't cancel that, or you shouldn't cancel that into 10. But the 2 is not under the radical. You can cancel the 2 into the 10. It will go 5 times, and that leaves you with the square root of 5 over 5. You cannot cancel these 5's because one is under the radical, one is not. They can only cancel if they are both under the radical or they are both outside of the radical. When one is in the radical and one is outside of the radical, They're different. You cannot cancel them. The square root of 72x squared. Remember, we said all our variables in this section are non-negative. They're 0 or a positive number. So when we think about this problem, we could think of it as, what's a perfect square that'll go into 72? 9 times 8. And we still have the x squared. What's the square root of 9? It's 3. What's the square root of x squared? That's x. Square root of 8, wait a minute. 8 is 4 times 2. I didn't get a big enough perfect square in there. I could have made it 36 times 2. I didn't see that. But I can still keep going and I'll get the right answer. 8 is 4 times 2. The square root of 4 is 2. Multiply that times 3, so we have 6x radical 2. And that's our final answer. So you don't always get the biggest perfect square factor. Sometimes you have to do it in 2 steps, and that's okay. So 8y cubed. 8y cubed. All right, let's think about this. 8 is 4 times 2. So that's okay. I can't take the square root of y cubed. I wish it were y squared, because I know the square root of y squared is just y. Can I factor y cubed into y squared times y to the first? Yeah, y squared times y to the first is y cubed. That's the same thing. So now I can take the square root of 4, that's 2. I can take the square root of y squared, that's y. I can't take the square root of 2. It's stuck under the radical. And y to the first is also stuck under the radical. So this simplifies to 2y radical 2y. 32a squared b to the 4th. 32 is 16 times 2. A squared I can handle. What about b to the 4th? Can I think of that as b squared times b squared? Yeah. So 16 is, square root of 16 is 4. I can't take the square root of 2. The square root of a squared is a. Now what's going on here? The square root of b squared is b, and the square root of b squared is b. So that gives me 4ab squared times the square root of 2. You don't have to think of it that way. You could say, what is the square root of b to the 4th? It's something times something. You square something, you get b to the 4th. It's got to be b squared, because b squared is b to the 4th. So b squared is the square root of b to the 4th. However you want to think of it, you need to get this as an answer. If a is a non-negative real number and b is a positive real number, then our quotient rule tells us that the square root of a over b is the square root of a over the square root of b. Just like we found out from the product rule that you can take the square root first, or you can multiply and then take the square root. Well, you can take the square root of the quotient. How about the square root of 36 over 9? What is 36 divided by 9? That's 4. So it's the square root of 4, which is 2. What's the square root of 36? 6. Square root of 9, 3. 6 over 3, 2. So it doesn't matter whether you take the square root and then divide, or divide and then take the square root. Either way is fine. So the square root of 9 over 25, we can think of this as the square root of 9 over the square root of 25, 3/5. The square root of 1 over 121, square root of 1 over the square root of 121, square root of 1 is 1, Square root of 121 is 11. The square root of 5 over the square root of 64. I can't take the square root of 5. It just has to stay the square root of 5. Square root of 64 is 8. Square root of 2 over the square root of 49. I can't take the square root of 2, but the square root of 49 is 7. Square root of 7 over the square root of 16. Can't take the square root of 7, but the square root of 16 is 4. What about this? The square root of 28 over the square root of 81. I can take the square root of 81. That's 9. What about the square root of 28? 28 is 4 times 7. I'd like to go ahead and take the square root of 4. That's 2. I still have a 7 under the radical, and I have a 9 in the denominator. So that's our final answer. There are all sorts of applications with radicals. You can approximate the distance in miles that a person can see to the horizon by multiplying 1.2 by the square root of a person's height, h, in feet. So express this relationship in a formula. The distance that a person can see can be found by multiplying 1.2 times the square root of the person's height in feet. Use this formula to approximate the distance a person can see from the top of the Sears Tower in Chicago, 1,353 feet high. So the distance is 1.2 times the square root of 1353, because that's how tall the person is when they're standing on the Sears Tower. What is that? 1.2 times the square root of 1353. Did you get 44 miles? A person can see 44 miles? 44.14 miles? That's a long way. It's probably going to be cloudy and you can't see that far. But if it's not cloudy, you can see that many miles from the top of the Sears Tower. Under certain conditions, the expression 2 radical 5L can be used to approximate the speed of a car in miles per hour that has left a skid mark of length L. If conditions were right and the skid mark was 125 feet, at what speed was the car traveling when the brake was applied? It should be BRAKE. So the speed in miles per hour can be approximated with 2 radical 5L, where L is the length of the skid mark in feet. So the speed, what's the speed when the skid was 125 feet? So we can put that in the calculator. Square root of 625 is 25 times 2, 50 miles per hour. The car was going approximately 50 miles per hour. I always wondered how they judged how fast the car was going from the speed, from the length of the skid mark. That's interesting. Pythagorean theorem. If you have a right triangle, this only works for a right triangle. Then the hypotenuse, the longest side, C, C squared equals A squared plus B squared. You can say it either way. Or A squared plus B squared equals C squared. The hypotenuse is the longest side. It is the side opposite the 90-degree angle. So C is on one side of the equation by itself. This TV set has a screen that is 11 inches by 12 inches. What's the length of the diagonal? That's a right triangle. The diagonal is the hypotenuse. It's the side opposite the 90-degree angle. It's the longest side. D squared equals 11 squared plus 12 squared. D squared equals 121 plus 144. D squared equals 265. What's the square root of 265? D is approximately 16.28 inches. Is that how they tell us how big a TV is, using the diagonal? Or do they use the length and the width? During the summer heat, a 2-mile bridge expands 2 feet in length. If we assume that the bulge occurs straight up the middle, how high is the bulge? Round to the nearest tenth. In reality, bridges are built with expansion spaces to avoid such buckling. Well, that's good news. Otherwise, I didn't want to drive across a 2-mile bridge in the heat of the summer. So we have created here, if you look at the picture, we have created 2 right triangles back to back. The length across the total distance of the bridge is 2 miles. So if we create 2 right triangles, then one of those triangles is going to be, the bottom leg is going to be 1 mile across. What is the height? That's what we want to know here. How tall, how far up does the bridge get pushed if it expands 2 feet in length? Well, if it expands 2 feet in length, now wait a minute, we've got miles and we've got feet. This is confusing. We need to either have just miles or just feet. I think it's going to be easier for us if we change everything to feet. But that brings up a troubling question. Just how many feet are in a mile? 5,280 feet. So the bottom leg of this triangle is 1 mile or 5,280 feet. Now, the hypotenuse of this triangle is the road where it has expanded by 2 feet and it is pushing upward. Well, if it originally, this part of the road was 1 mile long, 5,280 feet, if the whole bridge expanded by 2 feet, then half the bridge expanded by 1 foot. So this hypotenuse is not 5,280 because once the bridge expands by 2 feet, the bridge on, or the road on this side of the bridge will be 5,281 feet. So that's our right triangle. We need to solve for h. 5,281 feet is the hypotenuse. It's on one side by itself. That equals h squared plus 5,280 squared feet. Now I want to ask you, how far up do you think that bridge has buckled or been pushed? Just by expanding 1 foot over 1 mile on that side. What do you think? We need our calculators. So we have 5,281 squared. That's 27,888,961 equals h squared plus 5,280 squared. Ooh, that's 27,878,400. And these are large numbers. So what happens if you subtract 27,878,400 from both sides? You'll get h squared on the right 10,561 on the left. Take the square root of 10,561 feet, you get 102.77 feet. No way. Just a little 2-foot expansion over a 2-mile bridge shoves the middle of the bridge up into the air. 102.77 feet. That is scary. Thank goodness those bridges have the expansion panels in it to allow the swelling in the summer, allow it to take up the swelling instead of having it bulge upward 102 feet. That would be awful. That would definitely cause the bridge to fail. That's it for this section.